So, good afternoon, everyone. This is with a great pleasure that I welcome you here to the fifth Sustainability Lunch Talk, this time dedicated to solar cells and their contribution to the fight against global warming. Before I go on, I would like to remind you that this WebEx event is recorded and it will be made available on the Sustainability intranet page in the next few days. Please also ask your questions in the chat window. We will have a Q&A session at the end of the talk. So I am Laurent Bétry. I am the Sustainability Officer of the University of Luxembourg. I am in charge of integrating sustainability into the operations and functioning of the university. And one of the facets of my actions is to raise the awareness of the university community on the different themes of sustainability. This is why, together with the members of the Sustainability Coordination and Expertise Group, we have launched this series of discussion. This series is for everyone, committed or not. Its main objective is to restore the facts in the mass of information that is about sustainability. This is why we invite recognized researchers in the field to inform us in a short interactive format on the contributions of science to the questions we wish to address. And today we propose to address a more technical topic that in previous sustainability lunch talks, as already discussed in our previous talk given by Dr. Jürgen Jung from LIST on climate change modeling and local impacts in Luxembourg, the consequences of global warming are already visible and will be considerable. As you know, every tenth of a degree counts, and society, industry, and the economy are all seeking to promote the electrification of needs and to decarbonize the productions of goods and services. To do this, we talk about producing electricity from renewable sources, hydraulic, wind, biomass, and photovoltaic. The latter, due to its ease of installation and decentralization within the reach of almost everyone, appears to be the solution to our energy problems. Is this really the case? And how does a photovoltaic cell work? Is this technology up to the challenge? To answer these questions, we have with us Professor Susanne Siebentritt, Professor of Physics and Head of the Photovoltaic Lab at the Faculty of Science, Technology and Medicine of the University of Luxembourg. Her work focuses on the development of new thin solar cells and the semiconducting properties of the material used in these cells. This webinar will be hosted and moderated by Professor Niels Lundorf. Professor Lundorf is a member of the Department of Economics and Management at the University Faculties of Law, Economics and Finance. He holds the chair in digital procurement, and his work focuses on operations research, in particular optimization under uncertainty with current applications to energy procurement. Niels, the floor is now yours.
Okay, thank you very much, Laurent. And also from my side, welcome everybody to today's Sustainability Lunch Talk. So today we are going to take a closer look at solar cells. The IPCC, the Intergovernmental Panel on Climate Change, has long identified solar cells as strategically important technology to decarbonize the energy sector, which is a huge challenge on its own. And as we're going to learn, solar cells are attractive technology for two reasons. Photovoltaics can be deployed in a modular way almost anywhere on the planet. And the price of photovoltaic energy has fallen to the point that it can now compete with retail prices, meaning there are strong incentives for even consumers to invest into this technology by themselves. But generally, to better understand this topic, we would like to know today, how do solar cells help mitigate the climate crisis? And for this, we're going to take a little bit of a deeper dive into the technology and how it supports this very important mission. And to answer this question, we have Susanne Siebentritt with us from FSTM. Welcome, Susanne. Now, Laurent was already so kind to introduce Susanne, so I'm not going to add anything to that other than that she is very proficient and a leading expert in solar cells. She heads the photovoltaic laboratory at the University of Luxembourg, which she built up in 2007. And in that lab, she and her team design solar cells, improve their efficiency, and also study the physical properties of this technology. Susanne, we're delighted to have you with us today and walk with us through a number of questions. So first and foremost, what is a solar cell and how much electricity can we get out of this? And are solar cells generally even able to meet our electricity demand? And what are the ingredients for a 100% renewable system? Susanne, we are more than excited to hear your answers and more. And for the audience, please feel free to ask questions in the chat, and I will then try to synthesize these questions and ask them directly to Susanne. So please, Susanne, the screen is yours.
Good afternoon, everybody. Thank you, Laurent, for inviting me, and thanks, Niels, for the kind introduction. And if I can start my presentation. Too many windows here. Okay, this is what I meant to do. Okay, so the question, as Neil said, how can solar cells help to mitigate the climate crisis? And if you're following this sustainability talk, I don't need to say much about the climate crisis, but I would like to start with a short presentation from the emissions gap report that was published by the United Nations Environmental Program just before the climate conference in Egypt. And what we have here is the blue line is historical CO2 emissions with a dip in 2020 because of the COVID crisis, and now they're increasing again. And there are different projections. The blue projection is the current policies that are in place in the different countries. And then, as a part of the Paris Agreement, every country submits their nationally determined contributions. And countries can submit unconditional contributions, so things they promise to do in any case, and they can submit conditional contributions, so things they would do only if somebody else does something else. And the promised contributions that are on the table at the moment, and I think you all know the conference in the last climate conference didn't bring any improvements on that, is this is where these promises take us by 2013. So not much increase, but also not much reduction in the carbon emissions. And the lines that we have here are the lines that the climate experts tell us where we need to go by 2030, so in 8 years, to mitigate the climate crisis. And if we're happy to stay within a 2-degree range, which will cause already some havoc, we have already a gap, and we have a much bigger gap for the 1.5-degree warming. And the gap, so the least gap, if we're optimistic in the contributions and think we can survive a 2-degree warming, is 12 gigatons of CO2, and that's about 20% of the current emissions. So this is what we're missing in CO2 reductions. And this is what led Antonio Guterres, the Secretary General of the United Nations, to say we are on a highway to climate hell with our foot still on the accelerator. And to demonstrate the amount of the problem, this is the primary energy consumption of the world. Since 2070, if you go on our World in Data, you can see it since 1880. And one thing you see, the primary energy consumption is always increasing. You see 2 dips, that was the 2008 financial crisis, and that was the COVID crisis. But overall, energy consumption is increasing, and the largest part is natural gas, oil, and coal. And this is what we have to replace by carbon-free energy sources. It's not quite that dramatic as it seems, because this is the primary energy. So this is what we start with. And what we use in the end, there's the efficiency in between, and the burning something is horribly inefficient. So burning natural gas, oil, and coal to generate electricity, to generate movement is only about 30% efficient. So a lot of this primary energy that goes into the system, only 30% is used for useful energy. And of course, people are thinking about how to replace that. And the IPCC, the Intergovernmental Panel on Climate Change, published this spring their 6th assessment report. And part of this assessment report is a special report on mitigation. And the report is very long, but they always provide a summary for policymakers, and that's very accessible. And what is plotted here is the potential contribution to net emission reduction by 2030. And I just showed you we're missing at least 12 gigatons, and we could reduce about 4 gigatons by using wind energy, and about another 4 gigatons by using solar energy. And other big contributions come from carbon sequestration in agriculture. This is a different style of agriculture that actually puts carbon into the ground. By reduced conversion of forests and other ecosystems, so we just stop chopping down forests, and reforestation. And there is only one other big, I'm showing you only the first part of the graph, there's only one other big contribution that goes beyond 2 gigatons, and that's fuel switching in industry. The color code depicts how expensive that is. And I would like to draw your attention to the blue color. The blue color means that the costs are lower than the reference. So wind and PV are the most effective and the most cost-efficient options to reduce carbon emissions. And the cost numbers that the IPCC uses are actually a bit pessimistic, and I come back to that. So it's even cheaper than enters in these calculations by the IPCC. So I will not talk about wind, that's not my expertise. I will talk about solar cells. And so what is a solar cell? A solar cell is a device that generates electricity when we shine light on it. And I will give you a simple explanation on how a solar cell works. And I promise that's the only physics education I do in this talk, but I'm sorry, I'm a physicist and I love physics. So I'm sure you've seen these atomic models where we have the nucleus of the atom and the electrons of the atoms that are responsible for the chemistry. They are around the atom, and they are at different energies. You can imagine this like a ladder. On a ladder, you can only stand on the rung, you cannot stand in between. And these energies have to do with the distance of the electron from the nucleus. If we now make a crystal from many atoms, the electrons see not only their own atom, they also see the neighboring atoms. And then these energy levels become bands. So there are actually a wide range of energy where the electrons are allowed. But what remains is the energy gap. So there are areas in energy where the electrons cannot exist. And in a semiconductor, there is one band is completely filled with electrons. So nothing can move there, like sometimes in Luxembourgish parkings. And the next energy band is completely empty. So there is also nothing can move there. Now, if we shine light on the semiconductor, light is energy. And the electrons can actually take this energy and jump up to the next level. And then we have a gap down here. So the things can move down here. And we have an electron in the free space, so this electron can also move. Now, if this is all what we do, this electron will move around and will eventually fall back into the hole and emit again light or heat, and the energy will be lost. And if we make a solar cell, we add an asymmetry to the solar cell. We give the electrons a direction, so the electrons know which side to go, and by this we generate electricity, we generate current and voltage. And how we make this asymmetry, that's my day job. That's what we work on all the time. We do this by introducing an electric field, by making a p-n junction, or by putting selective contacts. And if you want to have more details, just send me an email. You're invited to my lab. So this is, in principle, how a solar cell functions. And so we get electric power out of a solar cell, and this is how much electric power we get out. This is measured by the efficiency. The efficiency is simply the ratio of the electric power that we get out divided by the power from the sun that shines on the solar cell. And the best solar cell so far has 47% efficiency. That's a very complicated device. It's probably the most complex optical device ever made in the world. It's made of hundreds of layers, and it's only a tenth of a square centimeter large. But it shows what is possible. And I'm waiting for the press release that somebody hit the 50%. I will be very happy when that happens. But that's not what we put in the field and what we put on our roofs. What we put in the field and on our roofs are solar modules. And they have an efficiency typically of 20%. And so some more, some less, but that's a reasonable average number. Now the sun shines 1 kilowatt per square meter if it shines. It's actually not so bad today, but it's a bit cloudy, so probably not 1 kilowatt per square meter today. But with full sunshine, we get 1 kilowatt per square meter. And so we get from a typical solar module, we get 200 watts per square meters. Now, the sun obviously in winter doesn't shine as much as in summer. And so what we need to take is the average over a year. And here you have a map of the world with a color code on how much sunshine the different areas have. And Luxembourg is here in the green area. That means we have on average 3 hours of sunshine per day, 3 hours of full sunshine. And there are areas where who have twice as much, like in southern Spain or in northern Africa. And there are areas that have 3 times more sunshine than we do, like in the Mojave Desert or the Atacama Desert or the Namib Desert. So with this average sunshine per year in Luxembourg, we get about 200 kilowatt hours per square meter and year. If you look at your electricity bill, you know what a kilowatt hour is. Typical electricity bill of a household is between 1,000 and 10,000 kilowatt hours. And so in Luxembourg, per square meter, we can generate 200 kilowatt hours per square meter per year with solar cells. In Spain, it's 400 kilowatt hours. So it's only a factor of 2 more. So this is certainly not an excuse not to install solar cells or PV in Luxembourg. I'm going to use a lot the word PV, which means photovoltaics, and it's just a synonym for solar cells. So how much solar cells, how much PV would we need to actually power Luxembourg? And so the total electricity consumption in 2001 in Luxembourg was 6,600 gigawatt hours. Giga is 1,000 kilo, so this is 6.6 million kilowatt hours. Now we get 200 kilowatt hours per square meter in year, so we need to cover this electricity, we need 33 square kilometers of PV in Luxembourg. And is that a lot? Is that horrible? Well, we can compare that with the area of buildings in Luxembourg, and that's numbers we got from our colleagues, at least from Laurent Gourdol. And the area of buildings in Luxembourg is 44 square kilometers. So if we only put solar on our roofs, and we could also use the facades, but if we put it only on our roofs, we could cover easily the current electricity need in Luxembourg. But that's on averaged over the year. And obviously the sun doesn't always shine. But fortunately, wind and sun are pretty much complementary. That's data from the International Energy Agency, and that's wind and solar generation in Europe. And you see here, the wind energy is more produced in winter, and the solar energy is more produced in summer. So the two are complementary. So obviously, in addition to PV, we also need wind power. And of course, we will also need storage and more grids, because we have here this temporal complementarity between wind and solar. And I showed you the map of the world for the sunshine hours. And the map of the wind speeds of the average wind energy is pretty much complementary, much more at the higher latitude and less at the lower latitudes. But that what I just discussed is the electricity that we need in Luxembourg. And we need more than electricity. And Niels actually helped me get the numbers. In 2020, in addition to electricity, we used 33,000 gigawatt hours of oil and gas. So if we add those 33,000 gigawatt hours to the 7,000 gigawatt hours of electricity, 44 kilometers of buildings will certainly not be enough. It's actually 13% of the area of the country that we would need. So do we actually need to cover 13% of the country with PV if we want to cover all our energy needs with PV? Yes and no. If we're serious about reducing carbon emissions, and don't import, I forgot to write that here, and if we're unable to reduce consumption. But for sure, we can reduce our energy consumption. One thing to consider is if we look at the energy, at the average energy per person per year in Luxembourg, that's twice as much as in the rest of Europe. This has many reasons. This has to do, of course, with the workforce being almost double the people living here. But for sure, we can reduce this. 20% of the energy that is used is actually for heating, and we can do something about it. And 50% is used for transport. Now, one thing to keep in mind is that electric motors are 3 times more efficient than combustion engine motors. And but if we plan to reduce our energy consumption considerably, it will not be enough to just replace all the cars by electric cars. In brackets, that wouldn't solve the traffic jams, which was horrible this morning. And so for sure, we need to do more. But we can for sure reduce our energy consumption. And if we do that, we could power the country by PV. And so we could. So where are we? How much PV do we have in the country? Now, according to the ILR, the Luxembourgish Regulations Institute, but right that in 2021 we produced 181 gigawatt hours of PV per year. That's 2.7% of the electricity. That's a bit sub-average. Worldwide, 3% of the electricity in 2021 was produced by PV. So if we look at the history, this is the total installed power. So you take the efficiency and the 1 kilowatt of sunshine and 1 kilowatt power of the sun per area, and then you get the installed power. So that's the capacity that Luxembourg can produce when in full sunshine. And yellow is the PV capacity installed, and blue is the wind capacity installed. So for sure, and that's over time. For sure, something is happening. And if we look in 2021, 90 megawatt were added, more than ever in history, and that is substantial. But if we consider we would like to produce at least all our electricity by PV, we would need to install by 2050, up to 2050, we would need to install 460 megawatt per year. So 5 times more than we did last year. That's a lot, but that's not undoable. It's doable. And but we need to do an effort, obvious. And so if we need to install all these power, all these solar modules, these solar modules need to be produced, and it takes energy to produce these solar modules. So is it even efficient? I mean, the IPCC seems to think that it's energy efficient to install solar modules. So let's look at the numbers. And one number we can look at is the energy payback time. And that gives you the time a module has to be in the field, in the sunshine, to produce all the energy that was used during its production. And this energy during its production takes the whole production chain into account, from the mining of the compounds to the making of the solar cell, to the shipping. It's included in the energy payback time. And this is calculated for a 19.9% efficient silicon module produced in China. So that's the average PV module that we have now. Most of the PV modules are produced in China, and the average is about 20%. And then you get here on this map the energy payback time in years. And it's in many places of the world, it's about half a year, the energy payback time. And but even in not sunny countries, like this is calculated for Belgium, it's a year and 4 months. And even in Canada, it's less than 1.5 years. And we can compare that with the manufacturer power output warranty. So this is 25 to 30 years. So the manufacturer guarantee an 80% power output warranty. So after 30 years, the PV module still produces 80% of its power. And that means at the end of the 30 years, you don't have to throw the PV module out. You can continue using it. And so for sure, the PV modules can produce on the order of 100 times more energy than is needed for their production. Now, with this energy needed for their production, there's of course, also linked. This is also linked with greenhouse gas emissions. So if we look at the greenhouse gas emissions from PV, and this is a recent study that compared different types of modules. This is a glass back sheet, so this has a plastic sheet on the back side, and this is glass, so this is a module between two glass plates, and made in China. China has a lot of coal electricity. Made in Germany. Germany also has a lot of coal electricity, or made with the average EU electricity mix. And you see, it depends on where the module is made, how much greenhouse gas emissions are generated with the with the electricity produced from this module. And if we now compare this with the greenhouse gas emissions of other electricity sources, this is an older study, also from the United Nations Energy Program, and they compare the greenhouse gas emission of fossil sources with wind and sun. And this is a study from 2016. At that time, they had available the data for the technology for 2010, and the red one is predictions they made for 2050. And if we compare now these greenhouse gas emissions with the predictions they made, okay, first what I should say is wind and PV are the only low carbon options that we have. CSS is carbon storage and sequestration, and it needs a lot of energy, so that it seems not to be really the solution. And if we compare with these numbers here, you hardly see it. So already solar modules are better than in this study was assumed that they would be for 2050. So PV continues to surprise the people who make studies. And so PV can mitigate climate change. But from the IPCC data, we also saw that it's one of the cheapest options. How is that possible? Because many people have heard that PV is expensive. Now here's a study made by my colleagues from the Fraunhofer Institute in Germany, and it's a busy graph I'll guide you through. What you have here is the levelized cost of electricity. You get to this cost by taking all the cost it takes to make the module, to install the module. Okay, this is for all power sources. So to install the power plant, and then the cost to run the power plant. Now, if you have a coal or gas power plant, obviously you need to pay for the fuel. We don't need to pay for the sun or for the wind. And then you take the lifetime of this power plant and how much electricity is generated by this power plant, and you take the total cost and divide it by the kilowatt hours produced during the lifetime of the plant, and this is the levelized cost of electricity. And we have here sun. This is just PV. The dark yellow is PV with battery storage. That's more expensive, but not that much. And what I also should say, what they compare here is new power plants. So if we're to build a power plant now, and then we have onshore and offshore wind, we have biogas, we have solid biomass, we have lignite brown coal or hard coal, we have combined cycle gas turbines or normal gas turbine. And what you see here, PV, large scale PV, so this is PV on a small roof, this is PV on large roofs, and this is a PV power plant is in fact the lowest cost the alternative to make electricity. So no, it's not too expensive. In fact, it's lower cost than any other new power station. So where does this come from? That and this is in Germany. So in countries with more sun, it would be even cheaper. And but somehow PV has the reputation to be expensive. If we look at the historical development, and that's the levelized cost of electricity, or the black dots are the historical development, and the gray line is sort of an average over this development. And the brown lines, the reddish lines, are the cost predictions by the IEA, by the International Energy Agency. And of course, they knew the historical data, and then they said, but now it will stop. Now there will be not much decrease in the cost, and they still say that. And it's again in 2019, their prediction is now PV will stop decreasing their cost. And the blue lines are AAM projections, integrated assessment models. And this is what the IPCC uses for their mitigation studies. And the authors of this study, they compare the rate of price decline predicted by the IAM models and the real rate. And over the history, the real rate has always been higher. So PV has always been cheaper than predicted and has decreased its price faster than expected. So how is this price decline possible? One reason for sure is an immense increase in the PV production. We measure the PV production in the power that a PV module can produce under full sunshine. And you see here an almost exponential increase, and 180 gigawatts were produced in 2021. And as already mentioned, these PV modules provide 3% of the world's electricity. The different colors are different technologies of PV. And so we added about almost 200 gigawatts last year, and sometime this summer, the total installed capacity. So when we add up all this production and take into account how long they exist, sometime last summer, more than 1 terawatt peak was installed, and that was an important milestone for the PV community. So one reason for the cost decline is the huge increase in production. That's just economy of scale. But there is more to it, and it's also the technology is developing. What you have here is, when you look at the red dots, that's the development of the module efficiency over time. And if we take an average, the efficiency of solar modules increases by about 5% points every year. And just as a side remark, the blue dots are the module power. So the module power follows the efficiency, and in the last years it has increased. That just means they make bigger modules. So this increase in efficiency will eventually hit physical limits. You cannot get infinite efficiency out from a PV module. So there are very basic physical thermodynamic limitations. And eventually this increase will hit these limitations. So will that then increase the cost per power? No, because there are new technological developments, and the hottest topic currently is tandem solar cells. That's from a paper from 2017, The dots here are the historical efficiencies for normal single solar cells and tandem solar cells. Tandem solar cells is effectively two solar cells on top of each other, and they use the solar spectrum better. And if you want, I can explain later more. So this is the single cells. This is small cells. This is what we can make in the lab. Now this is here the modules, and this is the line here is this 0.5% per year increase, and this is the different technologies. So this is based on a roadmap by the PV industry, and eventually this will level off because it will hit physical and practical limits. And the efficiency of tandem solar cells because they make better use of the solar spectrum, the efficiency increases can increase beyond these limits, and my colleagues here predicted something into the future. They were a bit optimistic. Here you see that the current record values for tandem cells, but they're improving and they're beyond the efficiencies of single modules. So new technological developments will will increase efficiency further, and PV will continue to be better. Now we said we need more PV for the energy transitions, and when you look in the latest World Energy Outlook from the IEA, they say clean electricity and electrification are absolutely central to the shifts to a net zero emission system. And of course, generating electricity costs. And I've shown you before that if we want to know how much the energy system of the future costs, we need to make predictions. And what I'm showing here is a study based on probabilistic predictions of the price development. And they looked into different transitions, the fast transition, the slow transition, and no transition. So we start here in all of them with our current energy supply that's based on coal, oil, and gas. And then they phase out in the transition models, they phase it out, and in other models, in other model, they don't phase it out. And I would like to draw your attention to the blue line. The blue line is the carbon emissions, and only the fast transition is compatible with the 2-degree warming scenario. And they also looked at the cost. And this is the probability for the cost of electricity in 2050. And the fast transition is, in fact, the cheapest, provides also the cheapest electricity. And this is because PV and wind costs are declining a lot. And what we have here is this green part. That's power to X. That's always very much disputed. Of course, we need fuels, and we make these fuels with electricity. So when we just look at the PV here, we come to about 30 terawatts by 2050. But we also need to cover this power to X electricity. This is fuels we make from electricity. And therefore, at the end, I would like to show you another study. This is a cost-optimized model. It's based on the... Yeah.
Susanne, sorry to interrupt. Yes. May continue. I just wanted to mention that we have a number of questions from the online audience, and we still want to have some time to answer those.
Okay, so I'm almost finished. This is based on the energy predictions of the International Energy Agency, and they calculate on an hourly basis to cover the energy need with different energy sources. And they also find that a lot of this energy needs to be covered by PV. So to summarize, the climate crisis needs mitigation, electrification is key, and PV is ready to power the world. And it's cost efficient. And if you allow me a personal statement, I think we need to do more. We need to reduce our energy consumptions, but let's make it happen. Thank you.
Okay, thank you very much, Susanne, for this convincing statement that we need to do more. And I think looking at your presentation, I think there is a lot of potential to do more. Now, there were a couple of questions coming from the audience, and I'm not going to ask them in the order in which they came. So first, what do you think? Are there enough raw materials to produce PV panels to become fully renewable? And what would be the environmental cost of doing that, of doing the mining? There are materials involved which can pollute the environment.
There are studies that look at the raw materials, and they come to the conclusion that it's challenging, that we have to reduce the material cost, the materials used in the solar modules. That's something that's happening anyway. But they come to the conclusion that even for models like this, with an increase in the energy supply, we have enough materials. Now, mining these materials, of course, also has an environmental cost. And the environmental footprint is of course not zero of PV and wind. But if you compare it with the environmental footprint of burning fossil fuel, it's similar to the ratio is similar to the carbon emissions. It's a lot lower.
Mm.
And
do we have sufficient mining capacity right now to produce that amount of material that is needed? Let's say we are on a path to 2050. We want to go from 3% to, let's say, 50%. We need to factor in primary energy use. Do we have enough mining capacity even and production capacity to provide the number of panels needed?
It's there was a recent study that actually looked at exactly that, and it's for all the raw materials that are needed for silicon modules, which is the main PV now. It's all within production capacity. So per year, one would need less than half of the current production capacity besides concrete. For the big parks, they put concrete basements. But concrete is very bad because it has huge carbon emissions. So the industry is switching to alternatives. They're using some ground hooks to fix the solar modules instead of concrete. But okay, because of this, I'm saying I think we need to do more. I'm not sure that this is the energy scenario we should go for. Maybe we need to decrease the energy that we use.
Another concern from a question that was asked in the chat was, what would be the environmental impact if we have more and more solar modules? So in that scenario, the energy from the sun is converted into electricity instead of generating heat on the earth. With this heat loss, would there be any unexpected environmental impact?
No, because I mean the efficiency is 20%. If we go to an efficiency of 30%, that's technologically within reach in the maybe next 10, 15 years. The rest is still converted into heat. And also we're not covering a considerable amount of the surface of the Earth. The sun shines more than 10,000 times the power on the Earth than we need. So we would convert a 10,000th of the sun power into electricity, so that would not be noticeable.
Mm. Then another question that came in was asked by Christopher Hansen. From an energy producer's view, how will PV be an attractive investment case if the total supply of PV energy in the market strongly increases in the future, but it can only be consumed when the sun shines? Isn't energy storage a necessary precondition?
It is. I mentioned that only briefly. We need storage, and the batteries have seen a similar price decline as PV. So the best way to store electricity on a short term, meaning over hours or a day, is batteries. And it's also the cheapest way. The studies need to take into account this decline in the battery price. And yes, we need storage, we need batteries, and we also need more long-term storage like hydrogen or other fuels that can also help us store energy, electricity, essentially, convert electricity into something that's easier to store over a longer period of time.
Mm. You spoke a lot about efficiency gains and said that efficiency increases by 0.5 percentage point per year. Wouldn't this also create a case for changing existing panels? Let's say panels that were installed 10 years ago, changing them in 20 years to accelerate the transition, because all the structure, the cables, the concrete, a lot of investment into the installation have already been made. Is this factored in this development, or even supported, subsidized?
It's not supported at the moment because the volume of PV that was installed 20 years ago is not significant. But it's the first feed-in tariff in Luxembourg is now coming to an end. So the question arises: what do we do with the old panels? Do we repower? And it's for the impact on climate and environment, it's very important what we do with the old modules. If we continue using the old modules and for some other applications and repower big power plants, it makes sense.
What about recycling the old modules? Is that easy, or do we basically have to give them a second life?
It's the technology to recycle PV panels is ready according to EU regulations. And EU regulation says you have to recycle, I forgot the exact percentage, 90% or so of the material. And that means mostly recycling the glass. And so this is ready. It doesn't happen a lot because, as I said, not many PV modules reach their end of life yet, but this will come and this will be a big business. And it's possible to recycle also the semiconductor. And I think this will become economical once the volume is big enough. At the moment, it's not economical. So at the moment, what they do is they recycle only the glass and they dump the silicon, which is a pity.
I also have a question. Suppose we want to install sufficiently many photovoltaics systems in Luxembourg to power the entire country, including producing fuel. How would that look like? How much capacity do we actually need? Factoring in the fact that maybe photovoltaics is not the only technology, we may also need batteries in the right amount and maybe substituted with wind. But what do you think would be the capacity needed, and where would it be located?
Well, if we assume we power all of Luxembourg by wind and PV, let's say half and half. And so if we take the energy we use now, we would need 13% of the country. If we take efficiency gains and by electrification into account, it's certainly less. As a measure, the airport is almost 1% of the country. So something on the order of 10 times the airport would be enough. It's not outrageous.
And then more of a fun questions. Do you know how much PV we have installed at the University of Luxembourg?
We have on the Maison des Sciences Humaines, there is PV installed. And I think Laurent knows more about this, but I think there will be PV installed on the bar of the Maison des Savoirs.
Okay.
This is correct.
And maybe Laurent knows the power of the system on the MSH.
I don't know that by heart, but what is nice is the screen that is available on the lobby of MSH that provides a lot of information about production, solar intensity, etc. So this is where we can find the information. This is also agreed with the panels also on the Maison de l'Innovation and also with the ROCAL. This is all together.
Laurent, what do you think? Do we have time for one more questions, or should we close the session in time?
If you have questions, you can continue.
There is one more in the chat. Susanne, you showed the negative impact of fossils for the environment. However, how relevant will nuclear power be for the energy mix in the future, in your view, especially in terms of baseload?
Okay, I just stopped the sharing, so I will start the sharing again. I was actually prepared for this question. So what about nuclear? Here is the data for 2021. Nuclear provides current. Okay, so first, in terms of emission, nuclear is clearly a low carbon emission. The emissions are in the range of emissions from modern PV plants. This is for the IEA numbers on energy in 2021. I showed you the development over time. So nuclear is the yellow one. It provides on about 5% of the current electricity, of the current energy need, not electricity, the current energy need. And we need to replace this much. And we need to replace it by 2050. And I showed you that we need to increase the electricity by, depending on the scenario and on how much we think we can save energy, of a factor of 5 or 10. It depends on your taste, if you think that nuclear can play a role there or not. But it's if we need a lot of wind and PV, and maybe this will be a part of this will be nuclear, but it will always only be a small part. And it's when it's the World Nuclear Association has data on the uranium supply in the current production, and when you take these numbers at the current production, uranium lasts for 127 years. If you think about a significant increase of nuclear to decarbonize the electricity, it will just not be, the known resources will probably not be enough. And it takes more than 20 years to build a nuclear power station. So we need to reduce by 2030, that's 8 years. So it's maybe in the long run, there will be some nuclear, but it will always only be a small contribution simply because we cannot build the new power plants fast enough. That's
okay. Thank you, Susanne. I think there are no more questions in the chat. I think I could continue asking questions about thin film solar, but in the interest of time, I will just continue this discussion with you some other time. Okay, thanks again, Susanne, for this very interesting, exciting lunch talk. Thank you to the audience for joining us today. And I think, Laurent, you also want to say a few words about the upcoming lunch talk, so I give the word back to you. Thank you.
Thank you, Niels, and thank you, Susanne, for this very interesting webinar. It was a very interesting insight in the technology and the connection to the Luxembourg gauge electricity energy consumption was very also insightful. So I hope that you enjoyed the presentation and the Q&A session. The recording of the talk will be made available on the Sustainability intranet pages in a few days. So it's now time to end the talk, and I would like to already invite you for the next Sustainability lunch talk that is scheduled on Wednesday, the 25th of January. Professor Michael Halling, who holds the university chair in sustainable finance, will join us to talk about sustainable finance, of course. So I wish you a very good afternoon and also a very happy holiday season. I'm closing the talk by thanking again Professor Siebentritt and Professor Lundorf for their excellent contributions, and I say goodbye.
Thank you. Goodbye.
Thank you.